In this video, we will discuss about interfacing a push button with ARM Cortex-M4 microcontroller GPIO available on TIVA C series LaunchPad evaluation kit. So let's get started. As a simple case study, we will interface the push button to the GPIO pin and program it to toggle TIVA C series onboard user LED. First of all, we will select the GPIO port pin for the push button, and then we will perform some configuration steps in order to configure it as an input. After that, we will see how a push button can be interfaced as an input, and the pinouts for the connection of the circuit will also be discussed. At the end, we will write the program and download it into the microcontroller and see a live demonstration. This is the schematic of general purpose microcontroller available on TIVA C series Launchpad. Out of 64 pins of the microcontroller, 43 pins are GPIO pins that are grouped in 6 labeled ports from port A to port F. But on TIVA C series Launchpad, out of 43 GPIO pins, only 35 pins are available. We can use any of the GPIO pin for interfacing the push button. Let's select port C pin 6 for interfacing the push button to microcontroller. For demonstration, let's select red user LED that is available on TIVA C series Launchpad, and it is interfaced to port F pin 1. By default, clock is disabled for all the GPIO ports. Therefore, the first step is to enable that clock. Whether you want to use entire port or few pins, we need to enable that clock on that GPIO port. Clock gating cycle register is responsible for enabling that clock to the GPIO ports. It is stationed at this memory address. Bit 0 to bit 5 of this register can be set to enable clock to port A to port F respectively. In our example, we are using port C for interfacing the push button and using a user LED that is available on port F. Therefore, we need to enable clock for these two ports. For that, we need to enable bit 2 and bit 5 of this register. So the corresponding hexadecimal value will be hex 24. After enabling the clock on GPIO ports, now we need to select the bus configuration. As we know, every GPIO port can be accessed using advanced peripheral bus or advanced high performance bus. The selection of bus is done by selecting the appropriate base address of the GPIO port. As you can see in this table, every port has two different base address, one for the advanced peripheral bus and the other one is with the advanced high performance bus. Let's select the advanced peripheral bus for accessing the port C and port F. Their corresponding base addresses are highlighted here. Every GPIO port comes with set of registers that are used to perform different types of configuration of that GPIO port. For all the GPIO ports, these registers have unique offset value, and their address can be found by adding this offset value to the base address of the port. First, we discuss about the configuration steps for port C, where we are interfacing our push button. So the mask value for the pin 6 will be hex 40. In mode control configuration, alternate function select register is used. In order to use the port C as a GPIO port, we need to clear every bit of this register. So the register value will be 00. The pad control configuration, the digital enable register is used. We need to set the bit of this register whose corresponding pin we want to use as a GPIO pin. In the data control configuration, we are using two registers. The first one is the direction control register. We need to clear the bits in order to configure that pin as an input. GPIO data register is the register that we will read in order to read the status of the input pin. For evaluating the offset for pin 6 of the port C, the pin 0 starts from bit 3. This is pin 0, pin 1, pin 2, pin 3, pin 4, pin 5 and pin 6. So this bit will be high and remaining all the bits will be 0. The corresponding hexadecimal offset value is hex 100. Now let's discuss these configurations for the port F, because the user LED is interfaced to the port F pin 1. This is the base address for the port F, and the mask for the pin 1 will be hex 02. As we discussed earlier, the alternate function select register value will be 00, and we will be using digital enable register in order to enable that pin as a digital pin. But in the direction enable register, you noticed instead of clearing the bit, now we are setting the bit, because when we need to configure a pin as a digital output, we set that bit in register in direction enable register. The offset value for the data register is also calculated as we discussed earlier. The only difference is now we want to access pin 1 instead of pin 6. Now we will discuss about interfacing the push button with microcontroller GPIO pin. The one important thing to notice for GPIO pin is that it can either read a low or high state. And if the push button is not interfaced correctly with the GPIO pin, the program will read a floating impedance state which is undesirable. So in order to achieve low or high states, we need to implement pull up or pull down resistors. The pull down resistors implements the positive logic, and the pull up resistors implements the negative logic. So let's see in some detail what these means. Here we will see the difference between pull down and pull up resistors and get to know why these resistors are important while interfacing a switch with the microcontroller pin. The pull down resistor implements the positive logic. What is meant by the positive logic is that when the push button is released, the GPIO pin is connected to the low state. That is, it is connected to the ground through the pull down resistor. And when the push button is pressed, the connection between the VCC and the ground is completed and the GPIO pin reads the high state. The pull down resistance is important here because in its absence, the VCC may be short to the ground and we can have a huge amount of current that can damage the GPIO pin. On the other hand, the pull up resistors implements the negative logic. In this arrangement, when the push button is released, the GPIO pin is connected with the VCC through the pull up resistor. And as we press the push button, the VCC is connected to the ground through the pull up resistors, and the GPIO pin reads the low state. Just like the pull down resistor, this pull up resistors avoids any kind of short circuiting. 10 kilo ohm can be used as pull down as well as pull up resistors. Let's write a C language program for push button interfacing. For that, let's use the Microvision Keil's project manager. Start new Microvision project. Go to the desired directory. Always create a new folder for your project. Let me call this push button interfacing. In the device for target, you need to select your device that you are using. This is the device name that is available on TIVA C-Series LaunchPad. In the manage runtime environment, we need to select core from CMS and start a file in the device. Hit OK. A new project is created. Initially, this project is empty and does not contain any source file. After changing the name of the target, let's add a C language source file in the source group. Hit add new file, select the C file, and let's name this file button interfacing. So this is the empty source file. Now we will write C language code in this source file. It is always help to add some comments at the start of your source file. This program will turn on the on-board red LED when the push button that is interfaced to port C pin 6 is pressed. Now let's add some macros defining different configuration registers and mask values. First of all, we have defined this macro for containing the address of a clock gating control register, and the second macro contains the value to be written on this register, and this value will enable clock only on port C and port F as we discussed earlier. The next set of macros defines the configuration registers addresses and mask for the port C pin 6. We have discussed these addresses earlier during our configuration step. Next, we have defined the configuration registers for port F, and after it we have defined macros that are required for generating the delay in order to implement switch debouncing. Now we will write main function of the C language. This is the user main program. First of all, we will enable the clock on GPIO port C and F. The next step will be configure port C pin 6 as a digital input pin. After that, we will configure port E pin 1 as a digital output pin because there is an onboard LED attached to this pin. After performing the configuration steps, we will want our program to execute infinitely. For that, we will need to add a while loop that is always true. So let's first perform these configuration steps. First of all, we will enable clock on port C and F. For that, we have defined this macro with _R. In order to turn on, we use bitwise OR operator with assignment operator. So this statement will turn on both bits in the corresponding the register address. Next, we need to configure port C pin 6 as a digital input. First of all, we need to digitally enable that pin. For that, we have defined macro GPIO port C digital enable _R, and for turning on we are using bitwise OR operator with assignment operator. Port GPIO port C pin 6. And in order to set the direction, we need to use the macro that is defined for the direction. And for setting a pin as an input, we need to clear that bit. It means we need to turn off that bit. For that, we are using bitwise AND operator with the assignment operator. Let me copy that. Since we are performing the AND operation, therefore we need to invert the mask as well. We are doing this for port F, whose pin 1 is used. Similarly, this will be port F and pin 1 is used. But the port F pin 1 is used as digital output, therefore its direction enable the corresponding bit will be set to 1. Therefore we need to use bitwise OR operator. So these are the configuration steps that are required to enable the both port pins as a digital input and output. Now we will write the program logic to turn on the onboard LED connected to pin 1 of port F when the push button is pressed. In this while loop, first of all we need to turn off the LED at pin 1. So for that we need to use bitwise add operator. This is bitwise AND operator with the assignment operator. Uh, we also need to complement. Now we will check the condition if the push button is pressed or not. For that we need to read this data register and check if it is equal to the GPIO pin 6 mask, and if this is the case we need to turn on. So for turning on we need to use bitwise OR operator and no need to use this complement. We also need to generate some delay. For that we can use a for loop. So now you can build the project. So you can see it is successfully building. Now we will see how we can interface a push button with TIVA C series LaunchPad microcontroller board. The TIVA C series LaunchPad had two type of connections: the male connectors pins on the top side and female connectors on the bottom side. We can use any of these two for interfacing the push button. The pins required for interfacing the push button are highlighted and labeled accordingly. The push button comes with 4 pins package, 2 pins on one side and the 2 pins on the opposite side. The pins on the one sides are in the open circuit format. As you can see, the pin A and C are on the same side, but they are not connected in the normally open mode of the push button. So you need to be careful while connecting the push button in the circuit. So let's complete the circuit and download the program in order to verify it. This is the circuit when we interface the push button with TIVA C series LaunchPad. The switch here is connected through a pull-down resistance. This brown wire is connected with the ground pin of the controller, and this ground signal is available over here. So this pull-down resistance whose value is 10 kilo ohm is connected with the ground, and then it is attached with the push button. The input GPIO pin is connected to this side of the push button. Since the push button is connected through the pull down resistor, so when switch is not pressed, we have logic low available at the GPIO input pin. So when we will press the push button, then the GPIO pin must read signal high. Attach your microcontroller with the computer and hit load button. So the program has been successfully downloaded. Now uh, let's press reset button. Now when we press the push button, you can notice the onboard red LED turns on. Whenever I press the push button, the LED turns on, and as I release the button, the LED turns off. So the switch is implemented using pull down resistor, as you can observe. The switch is pressed, LED is on, the switch is released, the low signal is read, and LED is off. We can also implement the negative logic. Means instead of using the pull down resistor, we can implement pull up resistor. As you can see in the circuit now, the GPIO pin is reading through the 10K pull up resistor, which is connected to the plus 3.3 volt VCC. So there is no need to change the program. We can download the same program into the microcontroller. The only change that we will observe, now we have implemented the negative logic. So without pressing the push button, the LED should turn on, and on pressing the switch, the LED should turn off. So first of all, press the reset button. You can see without pressing the push button, LED is turning off. So you can observe we have not pressed the push button, but LED is on. Now if I press the push button, you will observe LED turns off. It is due to we have implemented the negative logic by using the pull up resistor. The Cortex-M4 microcontroller that we are using come up with internal pull up and pull down resistors available to all GPIO pins, which means we don't need to use external pull up and pull down resistors. We can enable these resistor values by using pad control configuration registers. In order to enable these resistors, we just need to set the corresponding bit in these registers. For both these registers, these offset values are given, and we can easily calculate their addresses by adding these offset values to the base address of the port. Since we are using port C pin 6, therefore the address of these pull up and pull down resistor will be calculated by adding the base address of port C with their offset values. Let's see how we can enable this pull down resistor on port C pin 6. Let's add macros to define the address of pull down resistor. For that, let me copy paste this, and this is pull down register, and its address is 514. Also we need to enable this register. So using this register here, GPIO underscore port C PD, this register, and for setting we are using for turning on the bit we are using OR operation. Okay, this line of code will enable the internal pull down resistor available at port C pin 6. So there will be a little change in the circuit. You may have observed that there is no resistance involved because now we are using the internal pull up resistor. Now we are using the internal pull up resistors of the microcontroller. So let's connect the microcontroller with computer, uh, build the project and download the project. So let's press reset button, and now if I press the push button, you will observe the LED turn on, and as I release the button, the LED turns off. So we have implemented the positive logic by using the internal pull down resistor. Similarly, we can also enable the pull up resistor as we did with the pull down resistor. So let me call this pull up resistor, and its address is 510. So we just need to change this macro name here with the pull up resistor, and if we build the project, it's successfully built. On the circuit side, now we are using the internal pull up resistor. Therefore you can observe the digital input pin is connected to ground through the switch, and there is no VCC pin available because we are using the internal pull up resistor. So let's connect the microcontroller with the computer and download the program. Press the reset button. Since we are using the internal pull up, and the pull up resistor implements the negative logic, means when switch is not pressed, the LED will be on, and if I press the switch, you will observe LED turns off. Release the push button, LED is on, and if I again press the push button, LED is turned off. So this is the way how you can implement the internal pull up and pull down resistors. So that's all from my side. In this video, we learn how we can interface a push button with a GPIO pin with TIVA C series LaunchPad microcontroller. Thank you for your time. If you have any question, do let me know. See you next time.